Yep. So yeah, that's what we'll be focusing on. Just continuing on with where we left off, essentially. New
Yep.
question. Let's see. Screen share sorted. Camera sorted. Awesome. There's always going to be some functions relation stuff that builds up into it. Usually it's a bit of functions relations, bit of diff, and then finally getting a bit of the integration applications. I believe this is the last question for this particular SAC. After that, I don't know if we've... Let me have a quick look. Did we already have a look at integration chapter review? We might have done, but it's also been a while. Doesn't look too familiar, so we can move on to this afterwards perhaps. Anyway, let's start where we left off. Question 6. Okay. Find the values of n for which h is greater than 0. So, first thing you want to identify is what does n actually control as far as the function itself, even the domain perhaps. And then that can already give you an idea, roughly speaking, as to what likely constraints there are. This is also tech active, so using the CAS is also very valid. Oops. Did my square root wrong. X plus n minus n. Alright, a function is defined just in case we need it. What might we do? Find the values of n for which h is greater than 0. Oh yeah. Sorry, I didn't see.
I'm a bit confused with this question. So
Mm-hmm.
it says the values of n for which h of x is greater than 0, but there are well, there are two variables here. So
Yeah.
well,
There are. So I guess
how do I?
the spot that ends in, it's in a few spots. It's in the lower bound of the domain, it's in the plus inside the root, and it's the minus on the outside. If we think about like what translation factors there are, oh, I already kind of gave it away. What the n is doing here, it's translation factors of the root. So if we think about what that's actually doing, you've got if n is a positive number, for instance, as it gets more positive, it'll shift down and it'll shift left, right? If it gets more negative, it'll shift up and right. And so that's one thing you can do to try and get around having multiple variables in there.
I'm confused about the part that, like, it's a question asking for where, like, for what value of n does the function have only positive values?
Yeah, it's exactly what I was asking. For where
Okay,
does h of x be greater than
okay,
0 for all, yeah, for all x.
okay, that makes sense. Yeah.
Now you might be able to CAS solve this. We'll see. Sometimes it can be a bit strange. So solve h of x greater than 0, comma n. I don't know if that'll do it. Yeah, it does get a bit wonky with that. So the best way to go about it would be to typically draw it yourself, but even just chucking it on the CAS graphing tool itself and playing around with the sliders, you'll be able to see quite quickly what gets you positives. Like for instance n being 1, well already we can see it's dipped below. N being 0, we'll get right on that. Well, if I click it right, n being 0, we'll get right on the boundary. because you've got 0 vertical and 0 horizontal translation. And so we can essentially see that in the negative direction, starting from n equals 0. So even if we did negative 0.5, for instance, or not, or maybe there's just 2 decimals in there actually. Yeah, okay, I was going to say, didn't understand why that might not work. Yeah, anything left of n equals 0 is going to be good there. Fair enough. So that's a nice graphical way of going about that. Because the CAS solve didn't really help us too much, because as you said, there are multiple variables in there. So it did give us something. It gave us n in terms of x, which makes enough sense. But it also gave us a constraint around n also in terms of x in there as well. So trying to identify what it's actually saying is a bit tough. So best off just going straight to the graphing tool here and solving it that way. If there's any questions about that, let me know. Otherwise we'll move on to part B, finding the rule and domain of the inverse. To decipher the CAS outputs. So this one in particular, I wouldn't even bother trying to decipher at all. There's just too much going on, and it's not particularly useful either, because even if you do understand what this is saying, you've still got n in terms of x, which you don't really want. You would just want the values of n itself. As a brief, just sort of trying to understand what's going on here, we can pretty much easily rationalize that this n greater than thing would just be the rearranging of that inequality to get n on its own. You can see how, or imagine how potentially that might be the case. Now, as for where the numbers came from, that's a bit tougher. Can't really see too well where that might have come from. Max just means the maximum of either of those two values, so 0 or negative x, whichever is bigger, will be whatever that is. Keyword and, depending on how it's used, could be used in like a purely logical sense. The logical and just means if this is true and this is true, then true is the result. Whereas what it's talking about here, being used in the context of a lower bound of an inequality. Oh, it's actually not, sorry. The and here is more like the intersection that we would do in probability, where from my interpretation of it, you need both this to be true and this right-hand side set of inequalities to be true at the same time. Or to say, you wouldn't really want to try and interpret what's going on here. Better off going through and doing the graphical approach. And you know, where it is challenging to interpret but still worth doing, I'll definitely make sure to focus on that. Like for instance, it might even be useful, or we might get a bit of a strange result trying to do part B here, finding the rule and domain, if we try to do it via CAS. Because one of the things you can do with the CAS is actually solve inverses with it, with the CAS solve. Because if you think of what you do when you're doing inverse, you start by swapping the x and y and then solving for y. Solving for y is something that CAS solve can do. So if you do h of y, comma y, h of y equals x rather, so h of y equals x, comma y, you're swapping the location of it and then trying to solve for the unknown, you will get a result after that. Now, there is a bit of strangeness to it as well, where they've given an and in there as well. Again, this is like the the way to probably think about this one would be in terms of like rule and domain. So 2x take 1 being greater than or equal to 0, I would imagine has to do with the domain of it. Oh, I've just figured out where the numbers came from. It came from here. The fact that n is defined, which is why we're getting very specific results. Like if I replug in h of x, it'll make a bit more sense where these were coming from now, because the whole 2x minus 1 being greater than or equal to 0, that's just where the root is defined. So the inverse and the original function are still related to each other in a certain way. So maybe if I go ahead and kill the definition of n and do this again, we can see it's now purely in terms of the n term and the whole x plus n thing being greater than or equal to 0, again is just where is the root positive or equal to 0. That's where it's defined. So that's a CAS way of doing it. The other way, of course, would just be to rearrange it yourself, and it'll probably look better to do it yourself, actually, because in this case the CAS has expanded it and turned it into a full expanded quadratic, whereas you're probably going to get better results, usually with inverse functions, where it's not too bad. If you can see what the algebra would be like, you're usually better off just doing the algebra yourself. So let's see what that looks like. So we've got h is equal to square root x plus n minus n. First step of inverses is to swap the location of the x and y. X equals root y plus n minus n, and then rearranging for y. So in this case you're going to have x plus n all squared minus n equals y. Therefore your, I guess you'd call this h inverse to match up with the question. H inverse of x is equal to x plus n all squared minus n. And you can imagine if you were to expand this out, you'd get that n squared that you're looking for, which we saw in the CAS result here. Now this is obviously faster, right, and it is valid because it gives you both the rule and the domain, whereas at this we've obviously only got the rule. Fair enough so far. Any questions at all?
Wait, what was your simplification from the x to root y plus n minus n to the next part?
So I kind of did a lot in one go, that makes sense. So first plus n to both sides, that's this bit. Then you're left with the root, so you square both sides, that's this bit. And then you've got the plus n left over, so that's this bit.
Yeah, oh, okay, I see.
Yeah, kind of just did it all in one go there. And then yeah, if you wanted to, you could expand it to make it look like the CAS, but if you already got it on the CAS, you might as well just use the CAS version. And then yeah, as for getting the domain, if you were doing this in a tech-free way, then what you'd want to do is consider how inverses are related to their original. Does anyone remember the whole domain and range stuff when it comes to inverse pairs?
The domains and ranges flip.
Yeah, domain and ranges flip, exactly right. So if we know that the domain of h, the original function, is from negative n to infinity, then we understand that that means the range of this will be from negative n to infinity. Now that doesn't really help too much in the case of the quadratic, because, well, we can see based on the turning point form it's left n and down n, so we kind of already knew that. It's more so going to be thinking about the way this graph would look, as long as you can get a basic version of it, just some random substitution for n. Let's say we have this, right? No choice of n is going to change the fact that it's a root that's going up and right. It might shift left, it might shift down, it might shift right, it might shift up. It'll still have this sort of approach to it. Then, thinking about the fact that the inverse is the reflection in the line y equals x, we can now more safely observe what part of the quadratic we're likely to have. That's going to be the right-hand side part of the quadratic of the as of the turning point there. So when we give our domain, well, that's where it's going to come from. Any questions? Cool. So yeah, you've seen a few different ways of going about it. This is actually the first time I've seen the CAS actually give domain as well as the function itself, so that's a bit nice to see. So you've got that, and you've also got the tech-free way of doing it. Okay, next up. Oh yeah, question?
This might be a bit unrelated, but when I was doing my SAC this year, so I noticed something. Well, I was supposed to notice it. So the graphs that we were given, they were we had to find the inverse of it and stuff, and I did not know or never thought about it that the graphs can like the inverses can intersect outside of the y equals to x thing.
But they can or they can't?
They can.
How do they do that?
It was, I think, a square root function,
Yeah.
and when it, like their ends would touch. Like at one point, you can have 3 intercepts. So
At one point you can have 3 intercepts.
yeah.
Did you have it like pictured on did you see it on the graphing tool?
Yeah.
Do you remember what example you had?
Not exactly.
Okay.
Not exactly.
Because
I felt like mentioning it because, well, at least for me, we've never gone over that.
well, yeah, that's because from my understanding, it shouldn't be possible to intersect anywhere else other than on this line, if they're true inverse pairs, because they have to be mirrored, right? Like whatever you draw on, if we like invert it this way, whatever you draw on this side has to be exactly mirrored on the other side. So I can't imagine a way where you intersect, like let's say you want to intersect over here, like intersect in this spot. There's no real way to do that while still maintaining symmetry across the axis. So unless I can see your example, that'd be great, but
I don't know if I still have it on the class because I had to meet my class with my teacher. I don't know if she erased it or not.
Oh, sure.
Can I show?
Yeah, if you can.
Can I use the annotate too?
Yeah, go for it if you can.
I'll draw over here. So okay, so on my class, that's the
yeah, it's probably a bit hard to.
That's not. So that's going to be y equals to x.
Yeah.
And my graph was something like this.
Okay.
And at one point, these ends would touch, and there would be 3 intercepts.
those ends would touch.
So
How do they... So the only way... And this is a question you know you got wrong because of this, or...
no, I think I got it right. Yeah, we're supposed to get our SACs back this week.
Yeah. Because for inverses to exist, the functions have to be one-to-one. That's one of the key criteria for that. And just to try and maybe I'll redraw more or less what I'm seeing there, which is you have a root like this, and the copy of it is kind of... Okay, so if we're going to cut at 3 points, it'd be something like this, kind of. Now, for this to exist, that'll always exist. For these to also exist, how doable is this? Let's see. I'm going to play around with a few roots, and
Sorry, I just want to check what are we up to right now? I'm just
so part B is what we were doing, but we're just talking about a little bit of a tangent regarding how inverses work. So for the part B thing specifically, that was where we got up to with here, which was trying to find the rule and domain of the inverse function.
Yeah, so we're not up to C yet, are we?
No, not yet. But feel free to work on that if you want to. But we're currently just sort of having a look at a bit of a exploration into the inverse pairs.
Sure, yeah, I just wasn't sure if I was tracking right.
Yeah, that's fine. Okay, how come we're going to do this? Let's go ahead with... Let's just get a basic square root. If I can, jeez. Square root. Let's take 1 and the pair of that. So pretty sure it's going to be x squared. We're going to have x plus 1. Yeah. So let's give that a... Let's give that a domain. So that'll be x greater than equal -1. And that will get us one inverse pair there. Now, look at the line y equals x as well. Every time I click the tab, it keeps going to this. Let's get rid of that. Let's go y equals x. And, okay, from here, to try and explore things further. Okay, I think I can see what's going to happen. So if we go ahead and replace these with some n's, that really just create a new function. Get this one an n. And then just hide this. Let's see what we... Wait, go away. Really? Cool. Okay. Now, from here, is there a certain... Yeah, maybe there is. Getting a couple of intersection points. Okay. let's shift this over.
When I was doing it, all the intersection points were like on a line.
Oh, this isn't even a... this obviously isn't even an inverse pair then if it's doing this. Hang on. Let me solve the actual inverse properly. When you were doing this, what, sorry?
All the intersections were in a line.
Yeah, so like, if I redraw what you had, got this one, and then you'd have... Oh, it's hard to draw, isn't it? God. And like
Yeah,
all
it is a
the...
hard time.
Yeah, let's say you have intersection, intersection, they're all along the same sort of line that connects them. Maybe that's how I'll do it actually. Do it this way, dot 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 dot. Go axis, axis. We have dot here, we have dot here, we have dot here. How do we draw a route that connects all of those? They all existed on a straight line.
I'm not completely sure if they existed on a straight line, but from the looks of it, it looked like a straight line.
Yeah, okay. So I'm trying to... How do we draw a route that could do that? And I think my answer is that it can't. Unless... Nah, because then it's not touching there. Look, I guess I'll have to, rather than me mess around, and I feel like it'll take a while for me to try and replicate what you've got going on. If you can at some point show me what's going on there, then that'd be great.
Yeah, I've been searching my CAS. I can't find the original file.
But for now, just sort of based on my understanding of how things go, inverse functions should only ever exist when they're one-to-one. And so having multiple intersections beyond the line y equals x does seem a bit suspicious, because for it to intersect elsewhere, it feels like it wouldn't be one-to-one anymore. But I guess we'll have to have a look. Definitely curious to see it though. But yeah, anyway. Okay, cool. Next up, part C. So go back to the original functions that we had in the question. We had the square root again, finding the coordinates of the intersection between h and h inverse. Okay, so this is more or less what we were up to, or more trying to discuss, which is, can there be additional intersection points that don't exist along the line y equals x? So for solving part C here, it'd be a matter of either getting the two functions to equal each other, or you would equate one of them to the line y equals x. Now, it seems to be the case, if you've come across a scenario where they do intersect along other points than just y equals x, then where possible, making the functions equal each other is probably the best way to go about it then. But for the vast majority of cases, also equating to the line y equals x should also be fine. So, with that in mind, let's do exactly that. So, we've got our functions. I'm just going to borrow the one from the CAS. That is not menu 3.1.
Sorry, I just want to check it. So are we back on C now? Or?
Yeah, this will be C now.
Okay.
Okay, function 1 and function 2, which was just h. I'll fix up the n in a moment. Just going to get this down so we can get a copy of it later. Okay, and then quickly kill the n because we're using it as a slider. And now if we do it, we'll get them in terms of n here. So those are going to be the two x values for which they are equal to each other. You might also want to check and see, just to verify that the y values are also identical once more. H minus bracket and take 1. And then yeah, that's just the expanded version. So because I did say coordinates, you want to give both the x and the y. So all I was doing there was just verifying that those were indeed same. Right, so h of negative n still gets you negative n. H of 1 minus n is still 1 minus n. So at least in this case, we've definitely seen that those both definitely existed along the line y equals x, because that's when you've got the x and y being identical. Any questions there? Oh, saying is now you got a worksheet from school, could answer a lot. Yeah, send that through. We can do that either.
Yeah, I think I've attached it. It's like just in the message just above that.
If you have, it hasn't loaded.
I'll try send it again.
Yeah, give that a go. We'll finish up this because we've only got 2 questions left, and then we'll
Yep.
move on to that if it comes through. If not,
Yep.
Friday.
Did it come through?
Yes, it just did. That's good.
Okay, cool.
Cool. All right, let's finish this up. So onto the actual integration side of things now. Show the area enclosed by h and h inverse is constant for all values of n. So what does that mean? It means that no matter what you choose for n, the area enclosed by the 2 graphs should be the same. Not that it is a constant, that's a bit different. Being a constant would imply that it's just some value. Is constant, it's probably a bit of poor wording, so more realistically I think they're just saying that the area bound between them should be identical no matter what you have for the values of n. And if we explore what that looks like on the graphing tool, we'll probably just sort of see that that's what's going on. So we already have h. Let's go ahead and define the inverse as another function. So let's go I of x is going to be equal to this one. And then if we plot both of these, we should be able to observe what that bound area might look like. Okay. Plot h, create our slider. Plot I and give it a domain. So that one needed to be, oh shit, what was it exactly? I think it was just left of, or right of n. X greater than or equal to n. Let's see. Nah, that seems a bit off. Let's kill that domain and see what we, maybe negative n? Okay, that's a lot better. That's going to be the actual domain there. Cool, okay, so show the area enclosed is constant for all values of n. So far, just looking at what we have, the area enclosed is entirely underneath the x-axis there. Right, it's on the bottom side of it. Now, as we increase n, we will hopefully see that the area looks more or less the same for all the valid values of n. And based on what we just saw there, it looks like all it did was shift left and down. The net area seems to be the same. Do it again, seems to be the same. If we go negative, I'm pretty sure there's just going to be no more. Actually, there is still a bound area. Yeah, so just by looking at what's going on, it's kind of like we're just sort of shifting along the diagonal, the line y equals x there. Now, as for proving it, it should be a matter of determining that the bound area cancels out n and it becomes a constant. So if we think about how we do bound area between 2 curves, it's top take bottom. So in this case, the original, the root, is above the quadratic. And so when we do our definite integral, we should see that the n's cancel out. So let's see if that's what happens. It's going to be top take bottom, h over, or h take I. First, of course, we're going to delete our n so that doesn't play a role. We do our integral. Oh, actually, that's going to be a bit tougher because we've got to figure out the boundaries of it, which we already have actually. We know where the x-coordinates, the intersections are. We solved that earlier. We had here negative n and negative n take 1. So long as we make those our endpoints, we should be good. Negative n take 1, and it was h take I, because it's h on top, I on bottom. And in this case, yeah, comes out to be a constant value. Now that we've validated that, I don't know, because it is only 1 mark, show that. How much effort would it take to actually prove this? I don't even know if there's enough space in the test itself to go through and evaluate the full definite integral. So I think it'd be more so perhaps just showing this result is the best you could probably do. This wasn't a VCAR question, so let me pull up and see what the intended idea was here. What do they want us to do? Yeah, they wanted you to do exactly that, which was write out this integral and just say that it equals a third. Which is a bit weird for a show that. Normally you'd actually go through and do the actual algebra, but I guess whoever wrote this test thought 1 mark, so just give the idea of what you would do. If this is a VCAR thing, this would probably be a couple marks more, maybe a 3 mark in total, just me sort of spitballing how much complexity there might be in solving this integral, and then showing that the ends all cancel out, giving you a final answer of a third. Fair enough? Cool. Last question, hopefully not too challenging. If n is 0, figure out the value of q for which the average value of the inverse between... Okay, that's a lot of words. Average value of inverse is equal to average value of original. So average value of inverse is between 0 and q. Average value of the original is between 0 and 1. We want to figure out what q would have to be such that those average values are the same. So average value was mentioned a couple of times. Can anyone remind me how we find the average value of a function?
I think it was is it the formula is 1 over b minus a, and then it's, so I'm just writing it out so I can remember. It's 1 over b minus a, and then an integral bounded by b and a, and then just f of x.
Yeah, that's exactly right.
Right?
That's exactly what you do. Yeah.
Wait, is there a thing on the CAS for that, or do you just?
I was just typing that out as you said it.
Oh, okay. Or you just type it in yourself?
Yeah, correct. There might be a CAS inbuilt thing, but it shouldn't be too hard to just do Shift plus to get your integral, and then.
But that's probably like a UDF thing, right?
Maybe. I don't know. If we do A for average and we have a scroll, we might find something that says average. As for whether or not it gives you what we actually want is another story, but just from a brief scroll there, I didn't see it, though I did do it pretty quick.
Is the place where you are where you press the book button and then you go to section 1 and it has like the preset?
That's it. Yeah, it's the book button, and then you can press any letter on your keypad, and it'll take you to the top of that that spot.
Yeah, easy.
Cool. And if you're ever curious about what all of these do, there's a you can download for free the TI Inspire reference guide, which details what the syntax is and what each of the inbuilt functions do. I've done all the ones that you would care about in our CAS guide, but if you're really curious about what this thing can do, then that might be a nice little side quest. But yeah, okay, so average value, the B and A are the bounds of the integral, but they're also the upper and lower of where you want to actually evaluate your average value. So the one that's most immediately available to us is the average value of h, because we're given the upper and lower as x equals 0 and x equals 1. And we already know what h is, right? And we're forced with n equals 0. So we have all the parameters we need. We're just going to go ahead and evaluate and see what we have to now target. So it said do it from 0 to 1. That is a distance of 1. So we are trying to target an average value of 2/3 for the inverse function's average value. Because the whole idea is to say average value of inverse equals average value of original. We've now found our average value of original. So if we now need to do the average value of the inverse, well, it's the same thing. This time it's going to be in a CAS solve though, because we're going to make it equal to the value we just found, which was 2/3. That's not a 2. There we go. Now, I've already defined the inverse as I of x, so I'll use that. We already know the lower bound has to be x equals 0. The only thing we don't know is what that upper bound of q is. I'm just going to use a because we have a non-QWERTY keyboard, so finding things is annoying. I think that should be it. Let's see what we get. 2 to the power of a third. Seems about right. Let's just evaluate that just to be sure. So if we did 0, and 2 to the power of a third of I of x, do we indeed get 2/3? And the answer to that ends up being yes. Now, actually, I kind of screwed up here a little bit. I didn't do the distance right. So this should be 1 over a. That's a bit better. So we're going to get plus minus root 2 instead. Okay. Plus minus root 2. It says find the value of q. I've written a, of course. So only one of these is going to be valid. Who wants to take a stab at which one is likely to be valid?
Root over 2.
Yeah, root 2, the positive one. Why the positive one? If you've said something that didn't quite come through.
Negative.
Ooh, am I lagging or are you? Something's up.
Can you hear me now?
I can hear you, yep.
Isn't it, you can't have a negative area.
I don't know if it's necessarily about the negative area, because having the negative in the coefficient and on the integral bound should cancel those things out. It's more so the fact that we're told it's from 0 to this. So you would take the positive of that just because it's going from 0 to the right hand side. And we know from our exploration into what the quadratic look like that it goes from left to right, and so you would just take the positive. Mathematically, both of these work out, but we knew earlier that there were domain restrictions on the quadratic, on that inverse, so you would only pick the one that's right rather than left. Cool, okay, that's that. I think I got the download of your one, so let me have a look and see what we got. MHS worksheet. Cool. Do you want to point out the ones that you were having trouble with specifically?
Kind of like all.
Oh, that's sure.
I just,
Okay.
like I just kind of had like not really much of an idea of how to approach it all.
Yeah, that's fine.
Because I was feeling pretty good. I've been feeling pretty good about like diff and stuff, and then integration, I just have like no idea what I'm doing basically.
Yeah, no, that's no worries. Okay, so good news is these are all VCAR stuff, so I've seen a lot of this already. I remember this one specifically as well, which is, it's kind of like doing a rectangle rule thing, but they've kind of done it in the opposite way. It's like, well, hang on a minute, what the hell?
Yeah, if you could like explain everything, that would be...
Yeah, certainly. So maybe I'll still throw it back to you, which is, how do we do rectangle rule? Like, what's the whole idea?
As in the approximation?
Yeah, this approximation. Like, forget the specifics of this question. Just in terms of how we use rectangle rule to approximate area, what are we actually physically doing?
you're kind of drawing rectangles
Mhm.
that kind of align with the movement of the graph,
Mhm.
and then you're just calculating the area of the rectangles and adding them up.
Yeah, precisely.
So your estimate will either be under or below what the actual area is.
Yeah, exactly. So fundamentally, it's just finding the areas of a bunch of rectangles, adding them up. Finding area of rectangle means we need a length and we need a width. So based on what we're observing here, like let's say we want to find this rectangle on top here, right? We need to know what the length of this rectangle is and what the width of it is. The width of
Yep.
it is hopefully obvious to observe. What do we think the width is going to be? Width would be...
As in for the top rectangle.
Yeah, well, it's going to be consistent for all of them. The width is this length here.
Oh, 1.
1, exactly. All these have a spacing of 1. Nice and easy.
Yep.
Challenging part would be how to get this bit here. So this bit here, as far as how long it is, has an x coordinate down here, right? So what we need to do is figure out, okay, what is the x coordinate of this spot? We have the graph, y equals root x. That's the line that we're trying to do our area to the left of. So what this says is, where the y value is equal to 4, intersects here. So if I set y equals 4 and solve for x, I will get the corresponding x coordinate, thus getting this net distance. Is that fair?
Oh, okay.
Yeah, so it's the reverse. Instead of having your rectangles up this way, and you just
So you know that. I'm just gonna jump. So you'd know that it's 16 x there.
yeah, because square root 16 gets you 4.
Yeah. So that's just your length.
Yeah, so this one will have a length of 16, because as you can see, that's how far horizontally it would go, based on the fact that you have y equals 4. For 3, you'd have x equals 9. For 2, you'd have x equals 4, 1 and 1. Then you've got all the dimensions you need, multiply them all up, and then whichever they add up to is whatever they add up to. Probably not this fraction.
Okay, this question was way easier than I thought.
Yeah, for sure, but like, it's easy in hindsight, but it's also like, well shit, why'd they turn my bloody quadratic upside down? The first way that I solved this was not like that. The first way that I solved this was, I was like, okay, well on its side it's basically a quadratic, so what if I just do the quadratic and then take it from there? So when I did this the first time, when I was studying, I flipped this into a quadratic and then integrated, well not integrated, but did the rectangle rule normally from 0 to 4.
Wait, because did you do some of these questions when you were in year 12?
Oh, for sure, yeah. I went through at least 6 or 7 different sets of practice exams.
Oh wait, these are actual VCAR questions, alright.
This is VCAR
Wait,
2012.
ME2 just means methods 2. And then,
probably, yeah. I was kind of
then
just focused on this.
Yeah.
So this is the 2012 VCAR 14, the multi-choice 14.
Okay.
Yeah, all of these have their spot. And
Wait, do they still have multiple choice questions on
Yeah.
on the exam?
yeah, so
But
exam 2...
those ones you're expected to solve a bit quicker, right? You get a bit less time.
Yeah, so
Opposed to-
it depends on how you want to allocate your time. Usually you want to smash out as many immediate questions as possible. But if you just average out across the entire test, it's 1.5 marks per minute. Oh, sorry, 1.5 minutes per mark. My apologies. Because you just take the
Yeah.
test time and then divide by number of marks.
Yeah. Yep.
So yeah, if you want to think about it that way, sure. But ideally, just like any other question, you either just know what you're doing or you don't, and then just move on. Like
Yeah.
for this one, I would categorize as something that I would be able to spot quickly, so I would do this. For something like this, I kind of know what I'm doing, but I know there's a fair few steps involved, which is trying to rewrite this integral in such a way. I'll probably just skip that. Same with this.
Yeah.
But you're giving it to me, so we're going to do it. But just as
Yeah.
far as test taking strategy, do the thing that you feel like is pretty quick to get your free marks at.
Yeah.
But okay, so both of these questions are the same thing. We can kind of see similar structure, right? Which is we have a known integral in both cases, but we don't know what the function is. And from there, we have very similar integrals. In this case, they both have the exact same integral bounds on both. And, well, this one's actually a little bit different, sorry. This one also has an equals. In this case, we're trying to evaluate what the integral is. In this case, we're trying to evaluate what a would have to be. We're still following a similar procedure in both cases. This is where we use our integral properties to try and split things up in this right-hand side integral, such that it can eventually look like this left-hand side known integral. So if we think about ways of doing that, what things could we do to rewrite that right-hand side integral? Just changing it up a bit. Anyone can answer, by the way. If we think about our integral properties, there's a few things we can do to rewrite it different ways. I'll start us off. One of them is that because there's a minus between the two functions, 5 and 2f of x, we can split that up across two separate integrals. So instead of doing 1 to 4...
Is that just you do 1 to 4 of 5 and then 1 to 4 of 2f of x?
Yeah, exactly. That's exactly right. Just splitting it up into both of those. So minus 2f of x. Exactly, and this is exactly the same as what we just had. Nice. So this one is now fully solvable. We can just cas that out. It's not even that hard to do by hand, actually. So capital F would be 5x, and then you got 5 4s are 20 minus 5, so 15. It's capital F of 4, take capital F of 1. 20, take 5, 15. So that's that one there. This one, we still got to do a bit of rewriting because we need to make it look...
Alright, Chris, I just cut out for a bit. Could you reshow the integration for the first part again, sorry?
Reshow the integration for the first part. Yeah, so as in integrating this.
Yeah.
Yeah, so this is integral of a constant, and integral of any constant, you're essentially just slapping x on the end of it.
Oh, okay, yeah, that's the one.
Yeah.
Easy.
Then from there, definite integrals is always top take bottom, so capital F of 4 take capital F of 1. Substitute, simplify. From here, it's an f of x. We don't know how to anti-diff that. We can say capital F if we want, but that's not going to really help us getting our multi-choice answer. So what we got to do is try to figure out how we're going to continue rearranging that leftover integral until it looks more like, ideally identical to, the one that we do know what it equals. So to recap, the one that we do know equals something is 1 to 4f is equal to 6. So if we can make this look like 1 to 4f, then we know that's equal to 6. What can we do? This is currently 1 to 4 2f of x. So we've got to figure out some way to either remove or otherwise manipulate that too. It's the same principle as diff, by the way. And that is that any coefficients that are constant can come out the back of the integral. So in other words, you now have minus 2 integral of 4 to 1 f of x. So just so everyone can be on the same page, seems like we need a bit of a refresher on integral properties. I'll pull up the lecture content on that. Fundamentals and definite integral. Okay, so after looking at the actual definite integral side of things, if we have a look back at the screen share, you'll see that everything that I've just done is in one of these 6 properties here. The vast majority of you are only going to be focusing on 1 to 4. Some really annoying questions, one really annoying question that I've ever seen, uses a combination of 5 and 6. The ones that we just did are dot point 3, which is splitting the functions up into 2 separate integrals, and dot point 2, which is coefficients can be taken out the front. Just for your own study, you can see examples of all of these being used in well, in key examples. Here's a very similar thing, right? This was equal to that. Oh, sorry, this was equal to that. Figure out what this one is. Take the 4 out the front. Fair enough. I guess we'll finish it off. So, because we now have 1 to 4 of f, and we know that equals 6, we can now replace that whole integral with 6. That gives us 15 minus 12, which is going to give us answer A for 3. All good there? Okay. Similar idea over here. So again, we can see a plus between the two integrals, and we can see a coefficient on g. We're just going to go ahead and do a bit of rearranging. So first up, I will split, and I'll also take the coefficients out, the constants. So that's going to get us 0 to 5. We're going to have 2g of x. I'll just go ahead and put that 2 on the outside already. And the other integral is going to be a integral of 0 to 5 of just x. 0 to 5, just x. I should have put my dx's on there. And we know the sum of those is equal to 90. From here, we have 0 to 5g. We already know that's equal to 20. So we're going to go ahead and replace that with 20. 2 by 20, getting you 40. Plus the a integral from over here. That's going to equal 90. Again, using that same equation. From here, take them over, use the cas to evaluate 0 to 5, and then finally you'll have your a on its own. So let's just go ahead and do that. So we have 40 plus a times the integral of 0 to 5 x dx is equal to 90, comma a. That's going to get us a equals 4, which is why you can see b is highlighted. So again, similar idea, but this time it was already in an equation, so we're still just doing whatever we can to replace the g of x that's unknown with the value that we could replace it with, because constants are much easier to work with than unknown functions. That's how you solve all of these. Some combination of the definite integral properties. Mainly you're going to be spamming dot points 2 and 3, taking out coefficients and separating the functions. The more complicated ones are going to use dot point 1, and the really nasty shit ones are going to be using the dot points 5 and 6. There's only been one so far that I've seen. Okay, well, we've got time for one more. And this looks like a diff thing. Did you want to focus on the integration, or did you want to do this one as well?
Sorry, what was that?
Did you want to try this question 4? Or did you want to focus on the integration?
Yeah, I think I get the other ones. I think the first 3 is just I just didn't understand the question.
Oh, it's just the first 3.
Sense, but the no, I was saying just in general. The first 3 I probably should have got those.
Oh.
But question 4 I was pretty stumped on, to be honest.
Pretty stumped. Okay, so this one is a very repeatable kind of question. It's where you're trying to find an area that is inscribed into some other curve. We've seen this with like squares or rectangles inside semicircles. In this case, it's a triangle underneath a quadratic, right? Maximizing area. So we always know if we're trying to maximize something, we need to first find the thing we're trying to maximize. So in order, it's get your area function somehow, fmax it, and then either shove in the x coordinate to get the actual max, or give the x depending on what they wanted. Those are the steps. As for how we're going to do it here, first step, identify what your shape is. We have it timed, so if you guys need to go somewhere, feel free. Don't let me keep you, but we're going to finish this one off, okay? For those who need to go, I appreciate you coming. But okay, so this is a triangle. So what is the area of a triangle? It is half times base times height. So we're going to start there. The base, that is from 0 to m, so base is going to be m. The height, that is actually already given to us. Usually they force you to kind of think about it, but in this case they've actually given you the height, just 9 minus m squared. So we've got our half, base, height. We now have our area function. So let's do that. Function equals half times base times the height of 9 minus x squared. Okay. Of course, I'm using x's instead of m's. I'm just doing a quick change there. Half base height. Okay, from there, we're trying to maximize this area. F max. Or you can do diff 0, that's fine as well. I've just always defaulted to F max. Granted, if you're using F max, you kind of got to give a domain with it, otherwise it'll give you a nonsense answer like negative infinity. So if I have a look and see over what horizontal distance my questions are, my question has, it's from 0 to m. Right, we're not going to go anywhere outside that boundary. In fact, we haven't given m is between 0 and 3, oddly enough. So let's do that instead. 0 less than equal to x less than equal to 3. That's going to get us root 3. I suspect if I just did the x-intercept of the quadratic, that would also be fine as well. In fact, 3 is the x-intercept of the quadratic, so that's why they're giving it ahead of time. Now, if you're using TI Inspire like me, that is an x value for which there is a maximum. It's not the actual maximum. So to get the actual maximum, I shove that back in because this is my area function. 3 root 3, final answer. You'll see they've tried to screw you over by having part C as the x-coordinate for which there is a maximum, whereas what you want is answer D, the actual maximum. So as far as you catching up on how to do those kinds of questions, first up was the definite integral stuff. That's in the calculus tab in definite integral. As for the whole fmaxy kind of approach, that is also in calculus, applications of diff, max or min problems. So I'll pull that one up now. You can see here's an area trying to find value of x. Here's a triangle again inside a semicircle. Same sort of idea. It's bound by a shape. Do we have another one? Yeah, another trapezium. Minimum length. So this is where you can practice those similar kinds of questions. Okay.
Yeah. Would you say it's good to, like, say if I did this kind of test and I just like, I'm obviously going to be using the same bound reference you gave me for the next SAC. But I'm thinking of just like stapling a bunch of like random practice questions like these onto it.
Yeah, that was the advice I was given in school, which was, cool, take all of our resources and just bind them together, and then any questions you found unique and interesting that you want to reference, you can tack those on at the back. Yeah.
Yeah.
Now, did I use them? No, but
yeah,
they're nice. It's more of a peace of mind thing.
Yeah. Awesome. Thanks.
Cool. So yeah, these are good questions to be practicing because they show up all the time, so much so that I can even write a full guide on how you do it from start to finish. If you, well, I can't actually click it. If you see the top, it's, you know, very generic for all possible ways of going about it. Cool, that's about it. Any further questions, anyone?
How often did you...
Thanks, Chris. Over to go.
Yeah, no worries. Take care, Tyon.
How often did you actually reference the reference during the final exam?
Once. And I don't even know what I referenced it for. It was like a quick 2-minute thing to maybe find an equation. This is why I say it's more of a peace of mind thing. Because when you go into your exam, there's 2 possible outcomes. One is you're underprepared, and so you're spending pretty much all your time in the bound reference rather than answering questions. Not great. The other is you're very prepared and you only need the bound reference to quickly have a look at something you might have missed. And that's more or less what I was at, which was, it's like, okay, hang on, let me just refresh my mind on that thing. Got it. Cool. So you ideally, like, you don't need a big, massive bound reference because you're not going to reference nearly any of it. But you still want a big, massive bound reference because you want to make sure you've covered your bases and you've got exactly what you need just in case.
Yeah, my bound reference is like barren.
Yeah, that's fine. And what he was talking about, I recently updated each of the modules. So there's now a functions relations bound reference, there's a calculus bound reference, and there's a probability bound reference in the classroom stuff. And so if you want, you can just merge those three together, and that's your and that's your thing.
Okay.
Though it's a decently thick book.
Where is it?
Should be in all the major header of the modules. So like if you have you got the school website up?
Yeah.
Yeah, so if you just go like functions relations at the very bottom, bound reference.
Yeah, got it.
Yeah. Now like I did that on request. They're not as neat and nice to look at that most of my stuff is now. So just keep that in mind. They are big, massive, just sort of here's a snapshot of what my notes looked like at that time, and here's a bunch of practice questions that you can do.
I mean, mine's not going to be any better, so
Yeah, that's fair. But yeah, now you at least have something to use if you'd rather use that. It is probably a good practice to make your own bound reference anyway, so you know where everything is, and it's part of your study because you got to be practicing the stuff as you're making it. But you know, you need to have something just in case you can't be bothered, right?
yeah.
Cool.
Thanks.
Yeah, no worries. Thanks for your time.
Have a good day.
You too.
See you.
Take care.